Well, hey everyone, hope you all can hear me. Okay, so we'll be looking into the implementation of LRU Cache, a very interesting topic, and most importantly, it's a frequent interview question. So we'll delve into this question. This is slightly revolving around the domain of operating systems, but by the end of this question, you'll be, confident, you'll be certain that this is a DSLGO question. And the usual trend is that often the interviewer he wants to create a background of operating systems. He tells you about page faults and things, and then he poses the idea that okay, now let us solve a problem of operating system mixed with data structures, and he gives you this problem. Now there are many such similar problems, but this is one such problem, and it is it would be interesting to look at it. Okay. And just like many other problems, this problem shall also have multiple solutions. So it would be nice if you keep on rotating all the approaches in your mind. That will make it a more lively moment for all of you. So we are going to deal with the implementation of LRU cache, or we can say LRU page replacement policy. So let's wait for a couple of minutes maybe. We'll be starting in about 2-3 minutes. It's an interesting topic, so it will be nice to have some of you here. Starting in 2-3 minutes. So LRU basically stands for least recently used. I hope the screen is visible and I hope you all can hear me fine. So let's start at 6:33. Okay, so let's start. So whenever you are searching for something, suppose the value of a variable or maybe some page somewhere, whether you are searching in your local system or you are searching on the Google website, wherever you are searching, internally this is something that takes place. There is a portion of the system which holds, which basically is termed as your physical memory, which holds all the pages that shall be suggested or from where the answer shall be given to you. Now, this memory does not have the capacity to store all the pages, and for that reason, we have the hard disk to store all your pages, all your documents, separately. Memory does a single thing. What memory does is it only selects and keeps those pages in memory which you might be looking for. Okay, so in the next 5 minutes, if the memory thinks that you'll be searching a certain page more frequently, then it will prioritize that particular page while storing inside it rather than other pages which it will feel that you will not search for. So let us try to understand it. Suppose you are querying for these 341243102 and suppose in your memory you've got only three spaces. Suppose you have got only 3 spaces in your memory and you have to visit these pages. These are all different pages, page numbers you can say. So when you have to visit all these pages, for the first 3, in order to get the first 3 in the memory, they need to be stored in some manner 3, 4, 1. After that, when you want the second page, this is basic operating systems. When you want the second page, what it will say is, I don't have the second page. Please give me the second page from the secondary memory. So there will be a transfer of this second page from here to the memory. And it will say that replace one of these. It will replace either of this. You can say, depending on the policy, it may choose that I'll replace this page. I'll place 2 over here. And now we have 2 or 3 for 2. So the next one is 2, so you'll get 2 over here. 2 is going to be there. Next time you get 4, you can say, yeah, 4 is there in the memory. So it's fine. I can give the user what he wants. Then the user requests for third page. I can say that yes, this also I've got the answer. And then suppose I query for the first page. Now the system does not have the first page, because in order to bring the second page, it had to release the first page. So it said that, okay, now that I have to give the first page, so let me replace one of these elements with the first page. So it will replace one of them with the first page, and then this is now what the memory looks like. It will say that now I have 3, 1, 2. If you ask me any page 3, page 1, page 2, either of these, I'll be able to give just by fetching from inside my container. I don't have to request the hard disk for it. I don't have to request the specialized storage for it. I can give it from my own space. Okay. So you're able to give 1 whenever you bring this one. Then you face 0. So you'll say now 0 is not over here. So I have to bring 0, and if I bring 0, I don't have any space to store 0. So I have to replace whatever values I have over here by 0. So you adopt a policy, you say that any of them, based on my policy, any of them I'll be replacing by 0. So you say, okay, this is 0. So now I have 0, I can respond to 0 fast. Then I'll get 2. 2, I see that, okay, I have 2, so I can respond to this 2. Now I will get a request for 3. Now I don't have 3. So what can I say? Now I'll say that replace, bring 3 over here at any position, suppose over here. So you'll replace this by 3. And now, yes, you can respond to this in order one time. So this is basically the process. You basically have a number of pages, and at every point of time, you have to decide that which you'll be placing in memory, which one you won't be placing in memory. What is the idea? Suppose something like this. You have 3, 3, suppose something like this. 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 1, 2, 3. Something like this. What can you say? If I always possess 1, 2, 3, it will be the best for me, right? In order to process this. For only 4, I can say that just that single time, I can bring 4 over here, I can show it, and then I can again bring back 3, and then the entire process can go seamlessly. The benefit that we have is, if we have the proper elements or the proper pages in the memory, then the processing or the response is fast. And this is in the domain of data analysis, distributed databases and everything. The fast response is a very important aspect. And especially today, when you want the responses to come in milliseconds and microseconds and huge deal of applications being executed, what you want is the processing shall be fast. So basically what this LRU is? LRU is a page replacement policy. It is a page replacement policy which says that when you're getting a new page, a request of a new page, you basically need to take that page from the hard disk, whatever page it is. It may be some page titled as K. You need to take from the hard disk, and you need to decide which already present page in the memory you are going to replace with K. So idea would be that whichever page is the most unnecessary, I should replace with that. Whichever page I will not require most frequently, I should replace with that. So on this basis, there are many page replacement policies. Now, you don't know what is going to come in future. I'm talking about real life applications. The idea is that I should replace with something, I should push out something which I won't require much in the future, but you don't know about the future. So the algorithm goes something like this, that based on what I have seen till now, I will try to form my predictions. I will try to form my predictions, or I have to try to form my policies that which of the which element I'll be replacing. So there are many replacement policies. You can have some machine learning policy which will tell you that which of them has the least possibility of being visited in the next 10 intervals. You can replace that one. These are certain policies you can use. But there are some common policies. One of them is LRU. What LRU says is least recently used. Okay, so what this indicates is, suppose I'm doing this at time t. At time t minus 1, let us say at time t minus 1, I had used the page 2. At time t minus 2, I had used the page 3. At time t minus 3, I had used the page again 2. At time t minus 4, I had used the page 1. Suppose currently these are my pages in the memory. In the memory I have pages 1 to 3. So what can I say? I can say from here that recently these are the two things that are getting used. 2, 3 and 2. These are the two things that are getting used. And this one, this came more, the least recently. This came the most distant. This came a lot before, I can say. So from here I can say that 2, 3, these are the two pages which I have seen more frequently, or more nearer to the current duration. So that is the policy we apply here, that whichever you are seeing the least recently, you should remove that. This is the idea of LRU cache. Make sense? Just a second. Okay, so the basic idea is clear, right? What we are doing over here. Okay. So now the idea is, if you have this kind of a thing, suppose you have 3 spaces, let us simulate it. Let us see how this behaves. We have 2, we have 4, we have 3, we have 6, we have 2, we have 9, we have 8, we have 4, we have 2, we have 3, we have 4, we have 2, and we have 5, we have 6. Let's say something like this. This is our input. This is our input. So we can say that when we introduce 2, there is nothing, so we'll just place 2 in either of the boxes. We get 4, we are going to use 4 over here. We have 3, we can say now we have an empty box, so let us place 3 over here. Just a second. Jeff Bezos blasts off towards space. Really? Need to check it. Anyway, so after this, what do we see? The fourth element is 6, and 6 tells us that what elements I have in my memory, that is not sufficient. I have to bring 6, and if I have to bring 6 in the memory, I have to replace something with it. So what will I see? According to least recently used, I will see that out of these 3 things, this was the most recent page I had read, this was the next one, and this was the last one. This was last recently used page. So I had seen it the oldest. So I will say that, yeah, replace this 2 with 6. Next I'll see 2. By seeing 2, what will I say? That now, which is the least recently used? Among these 4, 3 and 6, 4 is the one which is the oldest, which you had read the oldest, most before. So we will replace 4 by the current element, which is 2. Then we face 9. We will see that among 3, 6 and 2, what are the last occurrences? I have read 2 the last, then 6, and previous to that I have read 3. So I should replace this 3. So you replace this 3 and you get 9. Similarly, you can understand, while we'll search for 8, we will again search that which is the least recently used. Recently used among 6 to 9. Among 6 to 9, 6 is the least recent. So you will replace 6 by 8. Now you come to 4, you will say that least recent is 2. So you'll replace this by 4. Now you get 2 over here. When you get this 2, you will say that Among this 984, which is the least recent, that is 9. So I'll replace this by 2. And now you see 3. So when you see 3, you will say that among 8, 4 and 2, 8 was the oldest. So I'll replace this by 3. 4 will come and 4 will say that okay, 4 is already there. I don't need to go to the hard disk for it. Now you come to 3. Now you come to 2. This 2. This 2 will say that out of 2, 3, 4, though 4 was introduced much before, but currently, which has been least recently used. This was introduced much before 2 and 3 were introduced. But 4 was used quite recently. But 2 was the last thing to be used. 2 is the oldest thing that I used for the last time. So I can say that I should replace 2. And hence it replaces... I'm sorry, by the way, we have 2 over here, right? We have 2 inside it. So we are going to retain it. When it comes to 5, we are going to make this analysis. That we have 3, 4, 2, which is the last one which we have used, 2. What is the second last one? We have used 4. Both of them had been introduced before 3. But 3 is the oldest one in terms of our sequence of usage. So we say 3 is going to be used now. 3 is going to be replaced now. So I replace 3 by 5. Now I can say when I need to replace something for 6, I will choose this 4 because this is older than 2. So I'll replace this and this is 6. Does it make sense? This is the basic, working of LRU cache. Do you want another example? Else we'll move on to the implementation of data structures for it. Okay. So over here nothing but what we are saying is that whatever has been least recently used, that has the least probability of being used in the next durations. This is the assumption that it works upon. And LRU cache, you can introduce any policy of your own, and you never know for sure that this policy is going to give us the best thing. What is the best thing? That algorithm which basically minimizes the number of page faults. Minimizes page faults. And what is page faults? Basically this replacement. So it should minimize the replacement basically. Okay. So some policy is the best if it minimizes the page faults. This is definitely not the best policy. LRU is definitely not the best policy. We can show a certain computation where LRU will perform the worst. It will give the worst value. We can show it. But anyway, but still it is, for average reasons, it is regarded as a good enough policy for your processing. So keeping that in mind, we'll proceed. And our intention is that given this definition of LRU, we have to implement it using data structures. So now the question, which is basically a very popular and quite frequent interview question, is implement LRU cache. Okay. Or you can implement LRU replacement policy. So what I will give you is, I will give you n numbers. You need to implement LRU and you need to tell me that every time what you are popping out, what you are storing, what is the status of the cache. You basically need to tell me. So I'll give you the n numbers and you have to tell me after every step that what is the status of the memory. So when I give you something like this, and I'll give you also the size of the cache. I'll give you the size of the cache. Because if the size is very large, then no replacement is required. But you have to basically implement it. So for given n numbers, which is basically a stream, you can treat it as a stream. What is stream? You have to do basically the queries online. What does that mean? That 2, 3, 4, when you will process for 4, that what is 4 going to replace? You don't know what is going to come next. So that is actually the essence of online queries, or something that stream does, stream of data. So it does not wait for the entire, what is that called? Block, or I'm missing the word. Batch. It will not wait for the batch of workload. It will say, I will read up to this part and I'll give you the answer for this part. Then I'll read for the next one, I'll give you the answer for this. So you have to give me approaches and you have to also analyze the time complexity of the approaches, because we are looking for the best approach possible. Up to here, I hope everything is fine. What are your suggestions for the choice of data structures or algorithms? What data structures can we choose over here? First question is, what data structures are useful? What data structures are useful for it? What data structures seem useful? This is the first question. Any suggestions? Okay. So let us see, if we just take an array, if we just naively want to do it, then let us see what happens. We have, suppose, the space filled up. Suppose we are using an array, okay, and the first few numbers which we are allowed to take, suppose we have filled up. So this is an array and we have filled up with, suppose, 4 pages, which is 1 2 3 4. Now suppose I get a page 6. So I can say, okay, now we are storing in sequence, so now 6 should replace this first guy. So I can say that because this one is the oldest, so I'll say just replace it, and I should place 6 at the end somewhere, because 6 is the latest one. So I'll say this is the oldest at the left and this is the latest at the right. So I'll definitely cancel out 1 and I'll say the new structure of the array should be something like this: 2 3 4 6. Now suppose I say that I'll be visiting 4, or I'll be visiting 3. Suppose if I visit 3, then 3 becomes the latest. So I should carry this to the end. I should carry this 3 to the end in order to keep the indication that this is the last thing that I have seen. So I'll carry this to the end and I can say it is 2 4 6 3, right? I can do something like this. Then if I say that, okay, replace by 5, I can say that, okay, just replace it and place 5 over here. Next time if I say that put 7, what can I say? That introduce it 7 at the end by replacing this. So you'll have 6 3 5 7. Now you see I have replaced 4. I have not replaced 6. 6 was introduced later than 4. But yeah, 6 was introduced later than 4. What we saw is that I have not replaced 3. I have replaced 4. You can see 3 is located over here. I have not replaced this 3. I have replaced rather the 4. Why? Because 3 I have used more recently. So I am removing only the one which has been least recently used. Okay. So what is the time complexity? So whenever this kind of a situation arises, why I am doing the second operation? Why I am doing the second operation? So that I maintain the chronology in my mind, that this is the order in which I should be removing it. So whenever I am visiting something which is already located here, I should carry that to the end. So first of all, whether something is located or not, I need to search it. I need to search it in my array. So that will take order of size. Suppose your array will store m elements. That is your cache. This is going to store m elements. So you can say it is order m. And you can say that now for carrying it forward, you again take m steps. So it will be clearly order m. It cannot be something better. What is our first operation doing? It is introducing a new element. When you introduce a new element, you say you have to replace something from the beginning. Basically, you have to replace the first element. You have to push all the elements to the left, and you have to push this element over here. This is what we can do. So here also we see that m steps are important. So this is the naive approach. For the n different pages, I can say that every step will introduce m steps in order to perform that step. So we can say the total time complexity is going to be n times n. If m is the size of the cache and n is the size of the stream, right? Size of cache and size of stream, that this stream that we are having, the data stream. So this is a simple array. What is another way? We can say that we can maybe avoid this deletion. We can say when we have this 1 2 3 4, this can store only 5. So what we can do is we'll introduce 6 at the end and we will leave it like it is. I don't care about what it is. I will leave it like it is, and I will just move the pointer, the start pointer which was pointing toward here, I will move it to the right. So now start points towards this one. This is gone. So now I can say that this is the end and this is the start. We can do something like this. Also, there is another way. If you think about the queue data structure, we can say that it will become far easier, right? Using queue data structure, what can I say? I have 1, 2, 3, 4. You want me to introduce 6. This is the queue front and this is the queue rear. So I will add at the rear. So I'll add 6 over here and I'll pop this out. This is the oldest. Similarly, when you say that I want to introduce 7, so you'll say I'll introduce 7 from the rear and I'll pop out 2 from the front. These are the elements which we are having. Now suppose I say that I want to read 4. If I have to read 4, the queue now looks like this. It looks like 3, 4, 6, 7. How many steps will be taken? Can we say it has to fetch it from here and it has to bring it to the rear? It has to bring it to the rear in order to right, in order to keep it at the earliest, that it is the last thing that it has read. It has to keep it over there. So there are two approaches. One is you maintain the hash set to indicate whether 4 is contained in your queue or not. Using a hash set you can do that. If it is contained, you will do this operation, that is carry it to the front. This will take order m steps and your hash set will take order 1. If not, then at every step, if you don't use a hash set, then at every step you need to do something so that the queue gives you an indication whether a certain page is present or not. You have to store something for that, some lookup table. Okay, because you have some cache, in order to tell you in order one time whether an element is present there or not, you either have to use hash set, hash map, something like that, or any of your own data structures. But you need something, right? So we have seen 3 kinds of approaches till now. One is simply array. We have seen simple array. I'm sorry. So I'll again. Yeah. So one is we have seen just an array. And using an array we have seen that deletion, addition, everything, whatever in whatever sequence we do, we are going to take n into m time. Remember, n is equal to the length of stream, and m is equal to the what can we say? M is equal to the size of the cache, right? The number of pages that the cache can hold at any point of time. So these are the 2 things. Now what can we say if this is the array? If you use an array to implement it, then you will basically require n into m operations. If you use an array with a hash map, and when I say array, you can also keep in your mind array list. You can do something. Okay, when you use an array with a hash map, you still require order n star m. Why? For this particular operation, if you say that a page which already exists, I want to take that forward. So for that reason, you need order n into m. If you use only queue without hash map, if you use queue without hash map, till now we have only seen a simple approach. Queue without hash map, then in order to see whether it is located inside, you have to pop out all the elements. You need extra space for popping out and storing, and there is a lot of difficulty. So it really does not make sense to have a queue without hash map. You rather can have a queue with a hash map. But in that case also, it is a problem. Why? Because whenever you talk of queue, I'll make it clear. Whenever you talk of queue, you basically say that this is my queue. Only these 2 elements matter to me. If I want to reach this element, that means these are not going to be taken into consideration later on. When you solve interview problems, whether you talk about sliding window maximum, or you talk about any stack based question, whatever you talk about, like your next greater element, previous greater element, what do you actually do in your mind? That after popping out, do I need this element? If I don't need this element, then yeah, I should pop out this. Which is a data structure that helps me to pop out? Stack. So use a stack. These are the things that you move in your mind. So if you require some value over here, you basically require to remove all these values in order to read this. This is the property of stack or property of queue. You cannot read in a stack or queue any value in between. You implement using an array and then you read it, that is the wrong practice. But in a stack or queue, you are only allowed to read for a stack only the top element, for a queue only the front and the rear element. So you cannot read any element in between. If you have to read it, you have to remove everything from behind. So a queue does not really make sense. But okay, if you remove everything and then you add everything, again it's the same thing. It will be n into m. That's it. It will be n into m. So these are the approaches we have seen. Can you think of any approaches? A very intuitive approach is whenever something is coming, I will store in my hash map the last time I have seen that. Okay? So using a red black tree, you can say the entire thing becomes quite easy. So what will you say? I'll maintain a red black tree or a I'll maintain a red black tree which will basically store all my current pages. You have faced this in a tree set. You might remember tree set, or you can say your ordered set. Ordered set in C++. If any term is unfamiliar, to you, please ask me, because this is a live session. Try to gain as much as you can from it. So tree set, ordered set, these help in storing certain values according to a certain property in a particular order. So based on that, you can reach any cell in order log n time. Or basically, if your tree, if the structure is of size m, if it is of size m, then it takes log m time. Okay, it takes log of m to the base 2 this time to reach any element and to delete any element and to add any element always. So if this is your cache, red black tree, or your tree set or ordered set, this is going to be your time. So you can say that over here I can do all operations now in order n log m. Makes sense? Why? For every element I will check that among the elements which are currently present, which is the one which has been least recently used. First of all, I will say that is this element present or not. I can find that out in a short while. So using a tree set and something called something like a hash map. What will the hash map say? The hash map will basically say what is the time when you have last seen this person, when you have last seen a certain page. So it will say for a certain page it has seen at a time t. So it will say, okay, search for the pair of pt, and if it is present, then update its time. So you are searching, you basically have to introduce page p. You basically have to respond to the user. User wants page p. So you will say, okay, I'll respond if it is contained in my tree. So you will see if in a hash map you have this p, you can ask him what time have you seen it. You will get the entire pair. So you will take this pair pt. You can search in your red black tree and you can update it. What will you update? That now it is no longer pt. It has got changed to p and the current time. Okay, this is the current time. So its time got updated. And now you say that, okay, now the user wants to see page q and page q is not located. So from my red black tree, I want to know which is the pair which has the lowest timestamp. Lowest timestamp indicates that it was the oldest visited. And I want to fetch that out, and I want to just throw that out. And I want to say just replace this page by that. Okay, this is the basic idea. Now this is just like as the intuition turns up, that for every page we should maintain the timestamp. This is a very common intuition. If you get this intuition and if you remain stuck over there, you can use this argument reset and ordered set to suggest an algorithm of order n log n. This will work. So this is an algorithm which is fine. The question is, can we do better? So the question is, can we do better? But this is something that we already have. So we have seen these 4 approaches. We have seen a 5th approach, which is using hash map and tree set. Okay, and tree set or ordered set in C++, which is basically red black tree. We have seen it will take order n log m time. Can we do better? While you think on this, you can ask me any question up to here. If you think how hash map will work here, how tree set will work here, whatever question randomly you have in your mind, or pseudo code, please. If you want me to write pseudo code, I can write a pseudo code. Whatever you think, please open up here, because we have sufficient time now. And now we'll come directly to the answer. But before this, convince yourself that up to here you understand everything. So any question regarding LRU Cache, how these basic approaches are going to help us, if you're confused about how exactly they are working, or if you're confused regarding anything that I've already said or already not said, you can ask now before we proceed to the main approach. So depending on the company, even this last approach that I talked about, this can also help you clear the interview. Okay, so it would be nice if you have paid attention and if you can state that you have understood it, or if you have any questions, you can ask me. So we are using a hash map to store all the pairs, all the pages which are currently existing in the cache and their corresponding time. So pi and ti, we are having this, and we are having a tree set to store those pages in the proper order of their current timestamps, latest timestamps. Okay, I'll wait till 7:07. If you have any doubts, you can ask me. Do you want some time to think yourself how we can maybe better it? Okay, so let's continue the discussion. Now we are doing basically a few operations. These are those operations. Deletion from middle. Think about our array based approach. So we are doing deletion from middle, or we are doing deletion from the start. Somewhere from start or middle means basically anywhere. We can do deletion from the start, which means that now a new page is being introduced, and hence, so this is when a new page is being introduced. New page is being introduced, we want to forget the old page. Middle means some already known page, some known page is being viewed. And the second operation which we are doing is addition at the front. Addition at the front, or addition at the rear, you can say. Addition at the rear. So these are the two operations, and what I know, this is order 1 operation, this is order 1 operation, this middle guy, this is order n operation, or order m, you can say. Okay, it is taking order m to fetch some element and take it to the end. Suppose using some structure I know where it is located. Suppose I know that in this array where it is located, I can reach there in order 1 time, and I know hash map can help me there. Hash map can tell me that for any given page, which index it is last located. I can reach over there. This thing I can easily do. So using hash map, I can easily reach that place. The point now settles at, when I know the location, how much time is taken to delete it. This is the only remaining part. How much time remains to delete it? So deletion from the middle is always order m for an array like structure. But can you think of a structure where deletion from middle takes order 1? Can you think of a structure for which deletion from middle is basically order 1? It's a linked list. So we can say here, we can actually say that if we know this particular element, which is I, if we know that our page is located over here, and here other pages are located, what I can say is that just take this, just fetch it from here, just fetch it from here and place it at the end. Okay, just fetch it from here and place it at the end and connect it over here, and this one you need to connect over here. So you need the address of the parent as well. In order to do this, you need its address and its parent's address also. As just exceptional case, just for the head, you would see that there is no parent. So if you collect only the parent's data, then you cannot finish it from there. So I will, just for safety, you can place both the parent and the current. Using these two things, you can say that if you store these two things for every page in a hash map, you can implement this using a single linked list. What about, think about a doubly linked list? Here you are storing two things, and going to the parent, making it link is a bit weird. So let us think about the other operation. Addition at the rear, it is easy. You can just add it over here. Deletion from the start, that is also easy. So this is your head. So now you say that this will become your new head. So this is your head, and you want to delete from the beginning. So you can say now this is your new head. So you'll basically delete this. You will see head is equal to head.next, and so you'll be done. So all the operations are possible using a linked list. The only thing is that just like you require the parent also, so that the parent can get connected to the next of the node that you want to remove. If this is the node you want to remove, then you require its parent and the next one, so that you can connect it like this. And suppose it is the head node, so you don't have any parent in that case, so you require to store the node in that case. So there are two such cases, but if you store the parent and the current, then you can basically do whatever you want. And now the conventional approach, the official approach is that we use a doubly linked list. Using a doubly linked list, what do we gain? We gain something like this. I'm sorry. Yeah. We'll use a doubly linked list. Where we will say that we have this kind of a structure. We have these pages stored. Suppose this is what my cache looks like currently. I have this kind of a structure. So I know that the first node is basically my oldest node, and this is my new node. And I'm querying for this X node. Okay, this X node, I know this is the node. My hash map tells me that this is my index. It tells me that this is my node. So what can I say? Suppose this is the node that contains X. This is the page. And this is the linked list that maintains it. When I'm choosing this, when the user asks this for me, what should I say? That now this is no longer the middle node. This should be the latest node. This should be the newest one. So I should take it over here. So this is A, this is B, this is C. What shall I say? I can get A by doing something like this, x.previous. I'll be getting B by doing something like this, x.next. And I can do so now that A.next equals to B. And I can do something like this, that B.prev equals to A. And I can say that X I'll place at the end. So x.prev is equals to C. I will require the tail over here. So it must be saved somewhere that tail is equal to C, whatever. There should be some variable tail. So I can say that yes, it is equal to tail. And tail dot next equals to X, and after this you will change the tail. You will say now tail points to the next thing which I've introduced over here, which is X. Right? This makes sense? That I can easily remove this and place it at the end, and this is basically going to be the operation. Thus only simple checking is that A and B, you need to check that they are null or not. If they're null, then you have to basically revise it. So if this will occur only if A is not null. This will occur only if B is not null. And we know X is not null. We know tail is also not null. There is at least some value over here. And yeah. So if this value is equal to tail only, then leave it like that. If X is equal to tail, then don't change it. Okay. If we see that it is not equal to tail, then yeah, we have to take it in front of tail. This is the idea. So what can we say? Now every operation we can see we have to delete from middle. We know we can reach the middle in order one time, and we can also delete it in order one time because we have a doubly linked list. After that we have to add at the end. Addition at the end, that is this particular operation, we can see that it easily happens in order one time. So we can just go to the end and we can just play with these pointers. These are the steps. So this is also order one. And there can be some cases when we have to delete from the start, in which case it is the oldest page. We want to like replace the oldest page. Suppose we say that this page is pretty new to me. I want to replace the oldest scene, that is the least recently used. I want to just throw that away and I want to introduce this page. So that will be one approach, like that would be definitely one step where we will require again order one time. Why? Because you know the start one. To delete something from the start, how much time does it take? Head equals to head.next, that's it. And head.next, whatever you have, that dot prev is equal to 0. So now the head gets updated. Whatever becomes a new head, its previous is going to be 0, and rest everything remains same. Makes sense? So do you have any questions up to here? So what we have seen is that using a hash map and a doubly linked list, using a hash map and a doubly linked list, I am taking only order n, yeah, only order n time you can say, or you can say order n plus m, but it will be order n. If n is less than m, then also it will be order n. Makes sense? What else? Hence, this is regarded as a standard approach. Without hash map, you cannot directly reach the position. So if you use only a doubly linked list, that is not sufficient. So only a doubly linked list will again take order nm time. Okay. So we have improved from order nm to order n log m to order n. Make sense? Very important interview question. It has been asked in many companies like D. Shaw and many other companies. Okay. Even very recently, it has been asked in some companies. So it's a very pertinent question. If you have any question in regard to this problem, please ask. There are 14 more minutes left, so you can ask any question. Code of doubly linked list. Code of doubly linked list. Okay. So let us see. I can show the pseudo code maybe. So first of all, you can have something like this. The first few nodes, for the first m nodes, you can say that we'll maintain it in a linked list. We'll have a list, we'll have the head and the tail. So what you will do is you will simply add the first m elements. It is going to be nothing different. So just add m elements. So the code of doubly linked list to add m elements, it is going to be over here. Okay. And after this m elements, what I want is the head and the tail should be there. After this only the code actually starts. Up to here you can use the templates of adding m elements. After that, what we can say is for I equals to the current element, which is basically you have taken up to m minus 1, 0 to m minus 1. Now we'll read from m up to the nth element in the stream, basically n minus 1, and we will say that we will take the value as input. So we will take this, suppose it is num. This is the, or suppose this is the page. So this page is equal to a of I, suppose in an array it is stored. And this page, we will first of all check whether it is there in the map or not. So these elements will be contained in the map, in the hash map with their indices. Okay. Up to here there is nothing as such. First element you take, you will store map dot like in the map you will place that the first element is in the 0th position, second element in the first position, and so on. That's it. Or basically in map what you can do is you will store something like this, that for this particular page you will have certain node. So the node will be saved. Okay. And you will form the doubly linked list. Now focus on this. You are getting the page and this is nothing but a page number. So you will ask if map dot contains key page. So you are checking whether in map page is contained or not. Now this is the Java syntax. I'm writing the Java syntax, but I think it is pretty legible. So in the map whether there is contained, if it is contained, then it will fetch the node. So the node or node x, we can say node x is equal to map.get page. Okay. Now what can you say? You know the head, you know the tail. You can say that first of all the previous one is going to be basically, or node prev, we can say node prev is going to, just a second, okay, Node prev is going to be what? X dot prev. This is the previous one. And then what? Node next is going to be X dot next. And then you can say that previous dot next will basically become next, and next dot previous will become previous. Okay. Over here there had to be a checking, but anyway we will do it separately. We'll do it later on. So next dot prev equals to prev, you have successfully deleted it. Now you have x separate, you don't have x over here. So now I'll say that tail dot next equals to x. You'll have x dot prev equals to tail, and you will have tail is now equals to x. Okay, makes sense? So this is the order that we are going to store in. So whenever it does not contain, or it contains the page, you are going to say that take it out and place it at the end. This is the hardest part. Over here there is only one assumption. There is only one assumption that this map.x, here the assumption is that x is not equals to head and x is not equals to tail. If it is equal to tail, it will remain the same, so it is the easy thing. If it is equal to the tail, we will keep it the same. If it is equal to the head, what will we say? That just make head the next guy and take it and place it at the tail. So this part will remain the same. The deletion part will change a bit. What will we say? The deletion part will become something like this. Basically, the previous one, this will be null. So prev, this thing will actually give null. So this operation you should not do. You should not do this operation. Rest of the things will be the same. Okay. So you can try coding it yourself, that part. So these are the two easy, base cases. You can handle it yourself. But this is the basic case. And then if this is not the case, if you enter the case where map does not contain this page, then what can you say? If it does not contain, you have to forget the oldest one which you have. So if you forget the oldest one, you need to say that node x, first of all, you are creating. It's a new node. I think, yeah, page. You will add map dot put. You'll put it over here. You will say that for this page I'll keep x over here. Next, once you place it at the end, you have to delete the first page. So you take the first one. You can say that node, this is to be deleted, so we'll say del, or you can say old. Whatever has become old, let us take it like this. So this is equal to the head. Okay. Now you can say that head equals to head dot next. Head dot next. Head equals to head dot next. And now head has become head dot next, so head dot prev equals to null. Make sense? So what you're basically saying is something like this. You are saying that this was the old thing. Now this was the head. You said that make this one as the head. Okay, and then make this as null. So now this will become null. It will forget this and it will become null. Okay, and now you need to say that map should basically forget. Map should forget map dot erase or delete or whatever you have, map dot remove, whatever you have. You need to forget this old, the content of this old. Okay, so from old dot data, maybe you can get the content. From old dot data or old dot val, you can get the content. You can remove it. So now map only contains whatever values are there in the list. But you have not added the node. You have not added this x. So now you need to add it, something like this. Tail dot next equals to x, and then x dot prev equals to tail, and you can say that after this I can say that tail is equal to x. What did I do over here? I basically said that here I have got tail, so attach x over here, and then x dot previous, attach it over here, and now forget that this is the tail, make this as the tail. So this is our new tail. Make sense? So now we have done all the operations here. The only things remaining are when x is equals to head and x is not equal to head, x not equal to tail. And yes, if there is only one element in the inter, like if the size is only one, in that case, what will you say? Then we can handle it separately. If the size of the cache is only one, we can handle it differently. It will be a very easy code. So those base cases you can look at. Other than that, you can see that this is a foolproof case. Any idea? Any doubts regarding what I've written here? Any particular line? You can treat this as line number 1, line number 2, line number 3, and you can tell me if you have any problem in any particular line. It is simple, right? Like whatever I mentioned, I just wrote it down. This is going to be your operation. So what is this? Order 1. Both the if and else parts are order 1. Even these things, these are order 1. So we can have all these steps in order 1. Adding of m elements, that is also order 1. So we'll have a total of order n plus n, or order n basically. Make sense? So we discussed the array approach. We saw that this deletion is becoming a bit weird, and also if I don't delete from the beginning, then this array size will go on increasing, and somewhere it will, I cannot store it. But over here you can see that only m elements are getting stored. You are not like storing n elements. That is why using that we first introduced q, and we discovered that we are not getting any any benefit. If size 1, then make single variable only good, right? Exactly. So if size is 1, then you can make. So usually for this kind of questions, I remember I was asked to run a certain problem. Like in code pair, I had given interviews where I had to run my problems on linked lists. But usually for this kind of question, people want to see how you choose the data structures, how you describe them, how you explain all the things, and how you compare against them. Usually they won't look for the entire code, but still, you should be prepared for it. For that reason, the only thing that I've missed out is how you'll do these things. These things should be easy, right? You're only adding m elements and you are parallelly adding it to the map. So only a single for loop that should do, right? So if I read out what I did over here, I created a node out of this page. If this page is not currently contained, then I added this to the hash map. I fetched the first one which needs to be deleted. I successfully deleted it and then deleted it from the hash map. Then I stored this new page into my linked list. With this I ensure that my linked list is always of size m. Okay. Similarly here what I have done is I have fetched the node from the middle. I have removed the connections with it over there. I have restored the connections between the two other nodes. And then I've come to the end and I've done the rest of the thing. Tail.next equals to x, x.prev equals to tail, tail equals to x. So in this way, my tail is also updated and everything is at its place. Here I can see the head is also updated. So everything is updated. I always have the head and tail at the proper place. You can see the tail is updated here. So the tail and head are updated after each of these steps. So these are the things that you need to stress in the interviews, if you ever sit in the interviews. Make sense? Okay, then I'll tell you shortly about the batches that are being offered at Unacademy. This is my profile where you can go and see my special classes. You can see the special classes for free. You can use my referral code Saptarshi1729. Basically this thing, Saptarshi1729. You can use this, and you'll be able to see all the classes, all the recordings, and the live classes as well. And apart from that, yeah, where were I? Okay, so I had this thing, copy, yeah. So it will be nice if you all are aware of the batches at Unacademy. These are 3 batches which are currently being offered. Mahayodha, which is a 2-month master course on advanced programming topics. I am taking this now. You have Eklavya 2.0, which is basically for beginners, but it will take you from beginner to advanced level, 8 months batch. And this is for college or off-campus placements. It is 5 months learning track. All have started on 6th of July. You have a structured learning path. You have 1 subscription, unlimited access to all batches and courses. You have the best coders of India's educators. And then in Mahayotha, you basically have this advanced mathematics. We recently covered this. Advanced dynamic programming, we have just started. Segment trees, advanced concepts of graph theory, mixed problem solving. Then you have Eklavya, where you start with the beginner level things, then the intermediate things, sorting and searching, basic data structures. You have all these tags, queues, linked list, additional concepts, greedy algorithms. And then you have square root decomposition, tries and segment trees, number theory, recursion, and dynamic programming. In Brahmastra, you have all the interview pertinent topics. Okay, so you step into sorting and searching from week 5, and then you have all the proper questions and topics that are covered in interviews. These are your educators. This is the old list. You have many more addition to them. You have live interactive classes. You have practice relevant problems at CodeChef, doubt support, and yeah. In 1 month you have to pay 6,000. In 3 months you have to pay 16,000. In 6 months you have to pay 27,000. In 12 months only 33,000. So you can see the way you require. You can see from 6 months to 12 months the price does not vary much, but it is quite discounted, and you can enjoy it up to a greater period, the subscription. So you can use my referral code Saptarshi1729 to get on top of all these rates 10% discount. You get a 10% discount on top of all of these. Okay. So that is it about myself. I usually don't speak much in sessions, but I am a 6-star rated coder at CodeChef. I have been a master at Codeforces. I have been to the ICPC, ACM ICPC regionals in 2019, and now I have cracked among the companies. I've cracked companies like Coordination and Google, and I'll be moving to Google quite soon. So that's about myself. If you have any questions, any comments, any feedback, any suggestions, anything, whatever you want to tell me, you can tell right now, or you can leave in the comment section. You can propagate to me in any channel, on any channel. So that's it. Cool then. Take care. Code it down if possible, and keep in mind the techniques that we discussed or how we approached, because the approach is also important for your interviews. So remember the approach, how we basically reach the answer. Okay. Cool. Take care. Let us call it a day then. Bye.